The sixth question that we have is a very interesting question. We have a capacitor with a charge of Q on this plate and minus Q on this plate, and it is filled with dielectric of dielectric constant K with a density of rho. Now what is happening is that this capacitor is slowly discharging through the dielectric. We need to find the time constant of the discharging. So we first assume a current I. It is discharging with current I. So what we can write here is that for this Q and minus Q, the current I is here. Now the potential difference across a capacitor can be written as Q is equal to CV. We already know that. Therefore the potential difference is equal to Q upon C. Therefore the potential difference across this can be written to be equal to Q upon Q. That is, let me write this for time t. Initial potential difference is Q upon C, the capacitor of this capacitor, the capacitance of this capacitor. Now after time t, let there be L charge over here and minus L charge over here, and a rate current equal to I. Now the potential difference across this, we need an equation. So we write the equation for potential difference. The potential difference across this can be written to be equal to L upon C. That is the capacitance of this capacitor, that is equal to K times epsilon naught A upon D. Let A and D be the area of cross section and the width of the capacitor. Because we know that when a capacitor is filled with dielectric of dielectric constant K, the capacitance becomes equal to K epsilon naught A upon D. This is the formula. This can be equated to the potential difference across. Now since there is a current I, we can write this whole dielectric is a resistance. Therefore the potential difference across the resistance, as we know, is I into R, where R is the resistance of the material. Now we can equate this to be I into R. That is, potential drop is IR, and that is equal to L upon K epsilon naught A upon D. The resistance can be written to be equal to rho L upon A, that is rho into D upon A. So we get the equation as the D upon A gets cancelled. So we get L upon K epsilon naught is equal to rho into I. Now we have an equation when I and L, where L is the charge on the capacitor after time t. Now what we can write is that we can write I is equal to minus dl upon dt. Since we had a plate of charge L and minus L over here and the current was in this direction, therefore this current is responsible for changing minus L, and therefore we have written I is equal to minus dl upon dt. On substituting it over there, we get L upon K epsilon naught is equal to minus rho dl upon dt. That is, dl upon L is equal to minus 1 upon rho K epsilon 0 into dt. On integrating both sides, we will integrate this from Q to L and this from 0 to T. On integrating, we get T minus T upon rho K epsilon 0. This is equal to ln of L upon Q, where L is the charge on the capacitor after time t. Therefore we get L is equal to Q times e raised to the minus T upon rho K epsilon 0. So we get the charge on the capacitor after time t as a function of t. Now we need to find out the time constant. We know that time constant is the term which comes below t in the equation, a e raised to minus T upon tau. Therefore tau is equal to rho K epsilon 0. That is equal to the time constant, and our answer for the time constant thus comes out to be equal to rho K epsilon 0. There is another way in which you could have visualized this question. This question could have been visualized as a capacitor C in series with discharging through a resistance R. These two systems can be treated as equivalent. Now we know that for this circuit, discharging circuit, the time constant is equal to R into C. Therefore we write down R into C. R is equal to rho into D upon A. Capacitance is, this is D, epsilon naught Ka upon D. This is equal to rho K epsilon naught. So we get the same answer by this method also. This is not very intuitive, but you can visualize this system as this, and thus solve the question directly by using the formula RC, which is the time constant for this discharging circuit. So final answer comes out to be equal to rho k epsilon 0.